Greetings everyone! We are back with momentum today. We're still looking at the file called 113_momentum01, and the next 4 videos will cover the rest of this set of slides. So this particular video will cover slides number 21 through 29 on that file. We're going to be covering 2 problems in particular. The first one is going to be a car collision, and then we're going to look at a rugby game. Then we're going to talk briefly about types of collisions, and then in the next 3 videos we're going to be doing some more example problems with those types of collisions. All right, if everyone goes to the conservation of momentum slide number 21 in the 113 momentum 01 set of slides, we can look at what we're doing today. And we start off noting that last time we discussed that if the impulse on a system is 0, then the initial momentum is equal to the final momentum. This is true of any system of objects. You can have a system, for example, of 2 cars that collide. If they collide, they're going to go off together somehow, and you can define the 2 cars together as being part of one system. So the momentum of the entire system of the 2 cars together before the collision and after the collision should be the same momentum. This is going to be very useful for all of our collision problems. We'll actually be using this conservation momentum, momentum initial is equal to momentum final. We'll be using that for every collision problem that we do. Every collision has this property. In fact, recoil also has this property. When you have 2 objects that separate out from each other very quickly, then that's called recoil, and that will also obey this equation right here. This is, again, only true when you can assume that the collision takes place over a very short amount of time, or if there's very few external forces pushing on these objects. All right, let's go to slide 22, and let's look at this collision problem. A 600-kilogram smart car going east at 30 meters per second strikes a 9,000-kilogram semi going west at 20 meters per second. The 2 stick together and have the same final velocity. We're going to need to set things up for this. First, though, I don't have a nice little smart car and semi. I've got these. So instead of little cars, I've got the UNSC Infinity, and I've got this little Vulcan science vessel. So we've got our 9,000-kilogram semi and our 600-kilogram smart car. The smart car is going east at 30 meters per second. Well, that means we need to switch these up. And so the smart car can go east. Always good to have these in the correct orientation. And the 9,000-kilogram semi is going west at 20 meters per second. This will not end well. The 2 will stick together and have the same final velocity. Okay, what do we know about this? We can draw this out. We've got our Vulcan science vessel / smart car at 600 kilograms going east at 30 meters per second. And we've got our semi, or our UNSC Infinity, going west at 20 meters per second with a mass of 9,000 kilograms. I'm going to name the smaller object the car, which I'll denote with a C, and I'm going to name the larger object the truck, which I'll denote with a T. The question on the slide is, to set up this problem, how many initial momenta do we need? Well, we start with this equation. I said that we can consider all these things to be part of a system. So if we consider our system to be both of these things put together, we know that before the collision to after the collision, the momentum should stay the same. So how many initial momenta do we need to solve this? I'll give you a second to think about that. And I hope you can see that we need to say that momentum initial is going to be the momentum initial of the car plus the momentum initial of the truck. And then the final momentum, same kind of thing, momentum final car plus momentum final truck. Well, this solves a whole lot of the problem for us right there. We can just plug these into the corresponding equation up there. We can say that the momentum initial of the car plus the momentum initial of the truck is equal to the momentum final of the car plus the momentum final of the truck. And then we can plug in the equations for all these. We've got the mass of the car, velocity initial car, plus mass of the truck, velocity initial truck, is equal to mass of the car, velocity final car, plus mass of the truck, velocity final truck. You see how this kind of gets more and more complicated as we go along. We know most of these things. We know the mass of the car, 600 kilograms, times velocity initial of the car. Well, it's going east at 30 meters per second, so I'm going to have that as being positive 30, plus the mass of the truck, 9,000, times the velocity initial of the truck. Well, it's going west, and so we need to say that it's going at negative 20 meters per second, because it's going the way that we generally define to be negative. We can make a little arrow saying that this is positive direction, just to remind us. This will equal the mass of the car, 600 kilograms, times velocity final car, plus the mass of the truck, 9,000 kilograms, times velocity final of the truck. Well, we've got one equation and two unknowns. That means it's completely unsolvable and we should just give up here and accept our failing grade. Or probably not. What do we know about the final velocity of the car and the final velocity of the truck? Well, the question says the two stick together and have the same final velocity. So I can just say that the final velocity of the car is equal to the final velocity of the truck is equal to the velocity final. So that will allow us to take some things out of there. We now have 600 times 30 minus 9,000 times 20, I just moved the negative sign around, is equal to velocity final times 600 plus 9,000. All right, I decided to get my calculator in here because I'm kind of lazy. So we need to solve for v final from this equation. So we need to figure out all these things. 600 times 30 minus 9,000 times 20. It looks like the left-hand side of the equation is going to be negative 162,000. What do you think the units are on that? This is just momentum, so they should probably be kilograms meters per second. And that's going to equal all this on the right, which is going to be 9,600 V final. And then we can divide this by 9,600 and throw in a decimal point like that and find that V final must be negative 16.9 meters per second. AKA, what do we say about that? Well, we can rewrite that as V final is equal to 16.9 meters per second west, because that negative implies that it's going the opposite direction, and that's going to be west. Slide 25 asks us, if the collision took place over 0.5 seconds, how much did each accelerate or decelerate? And I give you the reminder that the initial velocity of the car was 30 meters per second east, the truck was 20 meters per second west, and the final velocity was 16.9 meters per second west. And so to find the acceleration, all we need to do is say acceleration of the car, let's say, it's going to be the delta V of the car over the change in time. Well, the final velocity of the car, negative 16.9, minus the initial 30 over the time, 0.5, that is going to get us negative 16.9 minus 30 divided by 0.5 will get us an acceleration of negative 93.8 meters per second squared. That's pretty substantial right there. Well, what about for the semi? The acceleration of the truck will be the change in velocity of the truck over the change in time. That's going to be the final velocity, negative 16.9, minus the initial velocity, which was negative 20. So those are going to just add over 0.5, and we get negative 16.9 minus 20 divided by 0.5. Oh, you see what I did? See, I need to check too. I can't just plug these numbers in and expect to always be right. So, always check the numbers. Negative 16.9 minus negative, I was forgetting that negative sign, minus negative 20, 3.1 divided by 0.5. Acceleration of the truck must be 6.2 meters per second squared. You can see the huge difference that you get by being in the heavier vehicle versus the lighter vehicle. The lighter vehicle will experience far, far more acceleration than the heavier vehicle. Okay, next example problem. This is the rugby collision problem on slide 27. It says two rugby players, Alfred and Bruce, collide head-on. Alfred has a mass of 70 kilograms and Bruce has a mass of 80 kilograms. Just before the collision, Alfred was moving north at 5 meters per second, while Bruce was moving south at 6 meters per second. The players bounce off each other just a bit, such that after the collision, Alfred is now moving south at 1 meters per second. What is Bruce's speed after the collision? Well, first thing we should probably do is draw this out. We have Alfred and Bruce. Alfred is moving north at 5 meters per second. So we'll have Alfred here moving north at 5 meters per second. And Bruce was moving south at 6 meters per second. 6 meters per second for Bruce and for Alfred. Alfred had a mass of 70 kilograms and Bruce had a mass of 80 kilograms. This is the initial conditions. The final conditions will be such that Alfred, after the collision, is now moving south at 1 meters per second, still has a mass of 70 kilograms, and we don't know what Bruce is doing. All we know is that Bruce still has a mass of 80 kilograms. So we need to figure out Bruce's speed after the collision. All right, well, how do we begin every conservation of momentum problem? Remember, we did this all the time with energy. I always asked, how do we begin every conservation of energy problem? Now I'm going to be asking, how do we begin every conservation of momentum problem? This is going to be a little bit easier. We're going to begin every single one of them with momentum initial is equal to momentum final. This is fundamentally conservation of momentum right there. Well, what do we need to include as initial and final momenta? The initial momenta is going to be the momentum initial of Alfred plus the momentum initial of Bruce, and the final momentum is going to be the final momentum of Alfred plus the final momentum of Bruce. We can plug those in and say that momentum initial Alfred plus momentum initial Bruce is equal to momentum final Alfred plus momentum final Bruce. Go up here and say mass initial, or mass Alfred, because momentum is mv. Like that, we can say that the mass of Alfred times velocity initial of Alfred plus the mass of Bruce times velocity initial of Bruce is equal to the mass of Alfred velocity final Alfred plus mass Bruce velocity final Bruce. Now, what do we know? We know the mass of Alfred, 70 kilograms. Velocity initial Alfred, north, 5 meters per second. Mass of Bruce, 80 kilograms. Velocity initial Bruce, south, 6 meters per second. Mass of Alfred, got it. Velocity final Alfred, actually we got that too. It's 1 meters per second south. Mass of Bruce we still have, and final velocity of Bruce, well, that's what we're looking for. A lot of these problems are just going to be figuring out how to plug things in to look for one particular thing, especially if it's in one dimension, if it's in one linear kind of thing. Eventually we're going to get problems where you have collisions that are in two dimensions, in an x and a y, but right now we're just in one dimension at a time. So let's define something. I'm going to define up as positive, just to have something. Mass of Alfred, 70 kilograms. Velocity initial Alfred, positive 5 meters per second, plus mass of Bruce, 80, times initial velocity of Bruce, well, that's going to be negative 6, is equal to mass of Alfred, 70, times velocity final Alfred, well, that's going to be negative 1, plus mass of Bruce, 80, velocity final Bruce, which is what we're looking for. We can start plugging these things in. 70 times 5 plus 80 times negative 6 is going to be negative 130, and that's going to equal negative 70 plus 80 times v final Bruce. Then we can add 70 to both sides, and we get negative 60 is equal to 80 v final Bruce, and then we can say v final Bruce is equal to negative 60 divided by 80, and we get negative 3/4, or negative 0.75 meters per second. Or velocity final Bruce is 0.75 meters per second south. This means that as Bruce ran into Alfred, if we can use these cars for the example, as Bruce here ran into Alfred here, they were both traveling towards each other. It seems that Alfred got bounced off at 1 meters per second south, while Bruce was still plowing through at 0.75 meters per second south. So you can see that they probably bounced off a bit like that. This leads us to talking about 3 different kinds of collisions that we're going to be discussing this semester, this unit. We've got, broadly speaking, elastic collisions. In elastic collisions, objects will bounce off of each other and energy is conserved. Objects will bounce off of each other perfectly, and energy will be conserved and momentum will be conserved in their collision. So for elastic collisions, we've got delta P is equal to 0, and we've got delta E is equal to 0. We also have inelastic collisions. In an inelastic collisions, objects will bounce off of each other, but not quite as much. We've got 2 objects that come in, and instead of bouncing off with the speed that they came in at, they're going to bounce off quite a bit slower than they came in at. That is going to indicate that some energy was lost in the collision. How much? Well, you might have to do some math to figure that out. But what still works for an inelastic collision, and what works for all collisions, is that the change in momentum is still 0. Thus, of course, momentum initial is equal to momentum final, just like it's true up here, momentum initial is equal to momentum final. Finally, we can have perfectly inelastic collisions, and in these collisions, the 2 objects will come together and get stuck. They won't come apart afterwards, they'll actually be stuck together. And this is especially true in a lot of kinds of car collisions, or when you have 2 objects that somehow merge together after the collision. or stick together after the collision. In a perfectly inelastic collision, a lot of energy is lost. Not necessarily all the energy. You can always have a situation where you have a giant heavy thing moving quickly, like this, that'll hit a very light thing like that, and it's just going to push it away like that. The much heavier thing will win, even if the smaller object gets stuck to the larger object. That would be a perfectly inelastic collision if they get stuck together. Even in a situation like that, you're going to have the larger object still coming in with a great deal of speed. And so you can lose some of your energy, but you don't necessarily lose all of your energy unless the two objects stick together and stop. That's the only way you'll lose all the energy. But in many cases, you can have perfectly inelastic collisions where they keep going after the collision. And so in this kind of collision, you still get delta P is equal to 0. And of course, initial momentum will equal the final momentum. And you'll also know that V final of whatever the first object is equal to the V final of the second object. The two objects will have the same final velocity because they have stuck together. So, question for you, what types of collisions have we been talking about so far? I'm going to give you a few moments to think about that. Pause the video if you need to, and think about what kinds of collisions were the car and truck, and what kinds of collision was the Alfred and Bruce. Well, the two vehicles, the smart car and the semi, they stuck together, and so that must have been a perfectly inelastic collision. Whereas the collision with Alfred and Bruce, they didn't stick together. So for perfectly inelastic, they're going to stick together. If we're not told that they stick together, well then how do we determine if it's elastic or inelastic? We have to think, did we conserve energy or not? In that example, the two people running into each other playing rugby, well, they're coming in at some speed and they bounced and were going substantially slower afterwards. They started at 5 meters per second and -6 meters per second before the collision, and after the collision, they're at 1 meters per second and 0.75 meters per second, both south. So they must have lost a huge amount of kinetic energy in that kind of problem. And so that indicates that if they're combined, if their speeds are a lot lower after the collision, it was probably an inelastic collision rather than an elastic collision. See, that's going to be very hard to say. An inelastic collision versus an inelastic collision, an inelastic versus an elastic, very difficult. I'm going to try to enunciate very well when I mean an inelastic collision like Alfred and Bruce, or an elastic collision, which we have not gone over yet. So, the two vehicles were perfectly inelastic. Alfred and Bruce were just regular inelastic, and we will be discussing an elastic collision in the future.